मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we saw the potential energy theorem. We actually derived it by using variational principles. We also, in that process, saw the principle of virtual work, and we said that both of them are the same in the sense that we can get solution of a problem either by going through this potential energy theorem or through the virtual work principle. I hope you all remember, on one hand we derived potential energy theorem from the virtual work principle. On the other hand, we also said that if I have to go through this route, what is the assumption that we made? We said that strain energy should be defined, or in other words, for potential, as far as potential energy theorem is concerned, it is valid when this functional exists. In a more mathematical term, the functional exists. In this case, what is the functional? Phi p is the functional. In other words, the potential energy is called as a functional because it is the function of the functions, okay? And this functional exists only when strain energy density function exists, or in other words, for an elastic problem, we say that we can go through the route of the potential energy, okay? On the other hand, if you look at elastoplastic problems, then we can't derive the constitutive equation through the strain energy density. Then we have to resort to the virtual work principle, or in other words, our starting point will not be the potential energy theorem, but will be one step before it, that is the virtual work principle. We will see that later because we are going to derive some things now. So we will do that first and then come back to this problem of defining or determining the stiffness matrix, and when in that process how do we go about either from potential energy principle or from the virtual work principle. You have to wait for, I mean that has to wait maybe till next class. But before we go ahead, let us look at the problem that we did, or that we posed in the last class. We said that we have to derive, or we have to determine, what is this problem? I hope all of you remember this problem. This is one of our earliest problems that we did, right? What is that we determined? We determined U2 and U3. All of you remember this problem, right? Now my goal is to do that same problem by using potential energy principle, right? So you know what is potential energy? It is the strain energy minus the potential lost due to external loads, due to the work done by the external loads, right? U minus, say, omega. Let me write that as U minus omega. Omega is the potential, or minus omega is the potential lost. In other words, in simple terms, it is just P into D. P is the load that is acting, D is the displacement for that load, right? Okay, can you help me now to determine U? U is equal to, please note that I have already put for your sake 1, 2 and 3, okay? Now there are two ways in which we proceed, just a word of caution, two ways in which you can proceed. One is to look at the boundary condition at this stage itself. You can look at it like that and start writing down, okay? But for a bigger problem, this may cause a bit of a confusion. There is nothing wrong, but it may cause a bit of a confusion, okay? Why? Because actually the problem has it that there is a reaction that acts at 1. There is a reaction that acts at that point, or in other words, the potential is also lost due to reaction, but of course it so happens that the displacement at that place is equal to 0, and hence P into D term would be equal to 0. Is that clear? But nevertheless, in order to complete the picture, it's a good practice to write it down completely along with the reaction. So help me in writing that. So that's equal to half into K1, one of you can say that K1 into say U2 minus U1 whole squared, U2 minus U1 whole squared plus half K2 into U3 minus U2 whole squared minus P into U3 minus R into U1, where R is the reaction that happens to be present at 1. Is this clear? Okay. Now what is the next step? What are the now, what are my degrees of freedom? U1, U2 and U3. So phi p is a function of U1, U2 and U3. So what is that we do as the next step? Differentiate this with respect to ui's, right? Okay. So dou phi p by dou ui is equal to 0. Is that clear? Okay. So what happens to dou phi p by dou u1? Yeah, work it out, because it's a good practice. Instead of just following what I write, it's a good practice to just you write it down. Okay. So that will be half into K1 into, so u1 squared plus u2 squared minus 2 u1 u2. Okay. So the first term here will be 2u1 minus 2u1 u2, so minus 2 u2. Is that clear? Okay. So nothing will be present here, and then you will have minus r, okay, minus r, and that is equal to 0. Is it clear? Straightforward. So now write down what is dou phi p by dou u2. Dou phi p by dou u2. What is it? Yeah, you do that, you look at this here, look at this thing here, and then differentiate it with respect to u2. Maybe I think it's better to write it here so that you can see it here. Okay. So what will happen to the first term? Here also it is u2 is there. Okay. So differentiate it, and then differentiate, do the same thing with respect to u3 as well. Both of them are equal to 0. Okay, I'll give you 2 minutes, just do that and look at the result, and ultimately fill this up for me. So just do that and fill it up for me. So what will you get? You will get K1 there, minus K1, 0 here, minus K1, K1 plus K2, sorry, minus K2, minus K2 and K2. Look at that expressions now. Is it clear? Okay, what is this? Go back and, of course, that's 0. Go back and have a look at what you did in your earlier classes. Is it exactly the same? Right. Okay. So in other words, what is that you have done? You have got the same stiffness matrix first from equilibrium equation. Okay, remember that we got that from equilibrium equation. Now you have got the same stiffness matrix from potential energy theorem, right? What is here, by the way? R and minus P, because the directions are important, okay, minus P, R and minus P and so on, and so you can work it out. P, okay, R and P rather, R0 P, okay, R0 and P, and so R will, the direction of R will automatically be determined from this. I'm sure you can, or in other words, you can leave the first row, calculate the U2 and U3 from the second and third row, and you can get this thing going. Right, after this I think I can leave this problem. So I just wanted to show you that the same problem that you did earlier with an equilibrium equation can also be determined by means of this potential energy theorem. Right? Okay. I would like to do another problem. Okay? Now, the other problem is slightly more complicated, and I am going to introduce Rayleigh-Ritz procedure today. Any questions? Is it clear? Okay. Now, let's now look at another problem, and we will introduce what is called as a Rayleigh-Ritz procedure before we go into actually the finite element analysis, right? Let me look at the problem. Q is equal to Cx, okay, C is equal to force for L squared is C, okay. Determine the displacement and the stress and the strain. So that's the problem. Q is equal to Cx and C is some force per L squared, okay. Determine the displacement. Now, you have to first write down phi p, right? Now, what is this displacement? Displacement is now function of x. So, u is some function of x. Is it clear? Okay. Now, write down phi p first. As a first step, write down phi p. Okay, it consists of two terms, strain energy term as well as the potential that is lost due to external loads. So, what is the strain energy in this case? You know that half sigma epsilon. What is sigma? E into epsilon. What is epsilon? Du by dx. Okay. Now, this is integrated, this is per unit volume. So, this is integrated throughout the bar, right. So, I can ultimately write the first term of Ip as half 0 to L, okay, E into u comma x whole squared into A dx, that is all, A dx. Right? Is that clear? First term. What is the second term? Minus integral 0 to L u into what is now the force? Cx, okay, Cx into dx. Is it clear? So, force is u into Cx into dx, right. My whole job becomes slightly more complicated here because I want to find out now u as a function of x. Now, we will follow what is called as Rayleigh-Ritz procedure, which actually is a precursor or a pre-runner to finite element analysis. Okay. Now, what Rayleigh-Ritz did was to convert an accurate problem into an approximate, so or in other words he found out as approximate solution to this problem. What he did was that he introduced an approximate function for u. Introduced an approximate function for u. For example, a polynomial can be introduced for u. Okay, u is equal to say a0 plus a1x plus a2x squared and so on. Okay, and it was found that this polynomial should satisfy the boundary condition. Okay, in other words, u in this case happens to be a1x plus a2x squared plus so on. Is it clear? So he said that I will approximate u in terms of some polynomial function which is say a1x plus a2x squared plus a3x cubed and so on. That is the first step. Okay. Now what he did was to substitute this expression for u into the function phi p. Now what happens when I substitute like that? So this is an approximate solution. Remember that it is an approximate solution. We will comment about the solution later in the class, but right now let us say that what we want to do is to approximate u in terms of some a1, a2 and so on, right. So what happens when I substitute this into this expression, into phi p? Phi p will now become a function of a1s, a's that is a1, a2, a3 and so on. So in other words, in the previous expression or previous problem I had phi p in terms of u1, u2 and so on. Now I will have it in terms of a1, a2 and so on. So in other words, a1, a2, a3 can be looked at as a degree of freedom. That is correct. So a1, a2, a3 can be looked at as degrees of freedom. Is it clear? Yes. What is this degree of freedom? I know, I can understand that you immediately don't catch. There is no physical meaning to this degree of freedom. On the other hand, in my previous problem you did not have any doubts, because the degree of freedom was very clearly written as u2, u3 and so on, for which physical meaning was very clear to you. On the other hand, here I am writing it in terms of a1, a2 and a3, and hence you may have a doubt as to what this means, and that is one of the reasons why finite element method modified this Rayleigh-Ritz procedures and introduced this concept of nodes and degree of freedom with corresponding to the displacements at the nodes. Is it clear? So as a first step, let us see how to do the problem with say taking only one, u is equal to a1x, only one term. We will do that with two terms as well. But before that, let us look at the final result. Just write it down at the corner of your notebook, so that when you do this problem with a single or one or a1 alone or one term and then with two terms, compare that with the final result which I am going to give. The final result can be written as u is equal to c divided by 6ae into 3l squared x minus x cubed, 3l squared x minus x cubed. So that is the final solution or accurate solution or analytical solution, by solving this problem analytically. Now my goal is to get an approximate solution. In other words, whatever I am talking about, the equilibrium is approximately satisfied. It is not accurately satisfied at every point, but on an average it is satisfied. So the first thing is take u is equal to a1x, substitute it into this expression and see what you get, right? Okay, let us see how to do that. Yeah, any questions? Any doubts? Yeah, half into sigma epsilon. What is sigma? E epsilon. So half E epsilon squared. Okay, what is epsilon? Du by dx or u comma x. What is du by dx is what I write it as u comma x. So E epsilon squared becomes E u comma x squared. Is it clear? Yeah? Okay. Now u is equal to a1 x, that is what I want you to work on. So that du by dx becomes a1. Right? Is that clear? Okay. Now you have to help me. What is phi p? Half 0 to L E into a1 squared, right, into dx minus a dx minus the other terms. Okay. Now you fill it up, I'll just wait for a minute. Now I'm not going to do this problem, I'm going to give you some 5-10 minutes. Okay, let us see. What I want you to do is, I want you to do the first problem with this a1 alone, and then I want you to do the second problem with a1 plus a2x. Okay, let us get the results for these two problems, and then we will see, compare it with the final result. So before we proceed, just a minute. So you will write it in terms of phi p. The next solution is very simple. If you want, I can write that also. 0 to L, u is what? a1x into cx dx. Right? So it is a1x into cx dx. So phi p is now function of a1. Okay, right? Clear? Okay. Any questions?
A1 is constant.
No, a1 is not a constant, it is a degree of freedom. Okay, see, what it means is that u is equal to a function of a1 plus a2x, and I am trying to find out what is this distribution. See, whatever, please note this carefully, it is not a constant because whatever be the loading, I will write it in terms of a1 plus a2x. This is a polynomial irrespective of the loading condition. Is that clear? It is a polynomial irrespective of the loading condition, a1 plus a2x and so on. Now I will find out that a1 and that a2 which will satisfy the potential energy theorem, that is d phi p by dii, dou phi p by dou ai. Okay, what is that? That is what I am trying to find out. So a1 a2 is something like a variable. Okay, it is not that you can, it's a constant, whereas on the other hand, this form of the equation a1 plus a2x or a0 plus a1x plus a2x squared plus a3x cubed and so on, okay, that form is the same. Usually, okay, polynomials are used, maybe sometimes sine and cos functions can also be used, but 99% of the case it is the polynomial that is used. So a1, a2, a3 and so on becomes the degree of freedom, right? They are like u's, u1, u2, u3 and so on. Is that clear? Okay. So now what you do is differentiate that, this, then calculate dou phi p by dou ai or dou a1. In this case there is only one a, so a1, so d phi p by da1 and calculate a1, right? Okay, so that's the first step. Just a minute, before you proceed, let us look at the other one. The next problem or next step in this problem is to compare this result with two a's. What happens if there are two a's? That is a1 plus a2. So u is equal to a1x plus a2x squared. So that du by dx is equal to a1 plus 2a2x. Substitute it here, find out what the results are, and let us now compare the results with respect to 1 degree of freedom and 2 degrees of freedom. Or in other words, a linear term and the quadratic term. We will stop for 10 minutes and see whether you are able to work out this solution, and then later one of you can come and work out this, and then we will get some very interesting results to compare with the actual solution or analytical solutions. Okay, so you have had some 10 minutes time to work out. I hope you would have done the problems, but let us look at the first problem. Let me, for your sake, let me work out, or let me look at the first problem, or the first part of the problem. The first part, we had said that u is given by means of a1x. So substituting it here, okay, in this expression, so that du by dx becomes a1, and hence epsilon x whole squared becomes just a1 squared. Okay, I can write down phi p in this format. Then integrating it, so this term becomes, now this term becomes just L, right, and that term becomes, what is it, L cube by 3, okay, so that ultimately a1 becomes C L squared by 3ae, and note that d phi p by dA1 is equal to 0, and that is our initial condition for the potential energy theorem. Is that clear? Okay. Now let us look at the second part of the problem. The second part of the problem has u to be defined in terms of a1x plus a2x squared. In other words, what is that we have done? We have taken more terms in the polynomial, and all of you know that as I take more and more terms in a polynomial, okay, I can fit whatever be the order of u, I can fit, or whatever be the curve, I can fit it closer and closer, right. Any curve can be represented by means of polynomials. I go closer to the curve as I take many more number of terms, right. That is the whole idea. So you are right now clear that when I take more terms to u, then I will go closer to the solution. We are going to see that in just a minute. Okay. Now at this point of time, compare u, okay, with what you have got as the final solution or the accurate solution, or rather a solution that has been arrived at from analytical means, and then compare this also, okay, the stress and strain that you arrive at also with respect to the other thing. Or in other words, immediately you can realize, how do you calculate stress, by the way? So this is equal to, u is equal to a1x, right. So du by dx will give me epsilon x, and that is equal to a1, and that is equal to this expression. Okay, so CL squared by 3ae gives me the, what is that it gives? Strain, multiplied by E gives me the stress. So what does it mean? It means that now the stress, if I had taken, when I had taken one term, is constant throughout the bar, which is definitely rather an approximation, right. Okay. Now let us look at two term solution. Let us see how better this two term solution is, and let us see whether one of the students can come and work out a two term solution, right. Can you come? You can work out a two term solution. You can bring your paper, whatever you have worked out, and look at that. Write boldly, okay. Yeah, work it out as you've done. The second one, yeah. So you can point out if there is any mistake. Is it correct? A1 squared, what happens to this term actually? u comma x. U comma x is what? Dou u by dou x. So what is that here? A1 plus A2x whole square. So what is he writing correctly? So 4, so this is the second one, A1 A2x. So first term is right, okay. What is it? 2, yeah, 2A2x. Not x2, yeah, that's it's just x squared. Yeah, I didn't notice it, sorry. Right? 2A2 x squared. So second term is right, a1x plus a2x squared into c into x dx, right? Okay. So now integrate this. So first term becomes a1 squared into x. So that becomes, when I substitute for L, that becomes a1 L. Yeah. Yeah, you left out a1 squared. Yeah. Right? Is that second step? So now what is the third step? Now please note here that phi p is now in terms of a1, a2 only, right? Because we have already integrated it. So you can clearly see that phi p, like in the previous problem or previous discussions, is function of d1, d2 and so on. Now it's a function of a1, a2 and so on. So obviously what we have to do is to differentiate phi p with respect to a, that is a1 and a2. Dou a1 by 3. Right? Okay. Yeah, algebra can be quite complicated. You can't leave out any term. Is that right? 2a1 L plus this term comes from the 4a1 a2 L squared divided by 2. From that term you get that, okay. That is for a1. So similarly you write down dou phi p by dou a2. Okay. So dou phi p by dou a2. Yeah, you can take the side. Dou phi p by dou a2. Is it okay? Anyone has any objections to it? Right? No algebra mistake? You can rub this off. Okay. So, we get now two equations in A1 and A2. Just I think you can write down the final value of A1 and A2, you can solve for it, just get the final values of A1 and A2. Okay. So, you can write down the A1, A2 final values. CL squared by 12 AE, CL by 4 AE, yeah, A1 is CL by 4 AE, CL by 4 AE, and A1 is 7 CL squared by 12 AE, right. Okay. Fine. So, now how does this solution look like? Let us just draw approximately how the solution looks like and see where we stand with respect to the actual solution. Let us see what is the actual solution, how many terms are there, or what is the, I think I had written down already, I think I had a piece of paper. So, it is a, what is the solution? It is a cubic, right, in terms of x cubed. Okay. First let us plot u versus x. Let us say that is the correct solution, okay, or in other words that is the solution which has been obtained from analytical means, right. What is the solution for when we took only one term? It is a linear solution, okay, and hence that is what, if I plot it, that is what I would have got. And the second term solution is actually very, very close to the actual solution and looks something like that. Okay. So, in other words, as I take more and more terms, what is that I do? I approach the actual solution. Okay. Now, let us see how the stress plot looks like. Okay. Now, what would be the stress plot for the first case, that is for the actual solution? Will it be a straight line? What is the stress plot for the actual case? It is in terms of x cubed, so it will be a quadratic, right. So, the solution would look something like this, sigma versus x, right. Okay. Now, how would the first thing look like, or the first solution or first part of the solution? It would be a constant. So, it is like this. And the second one, what about the second one? It would be linear, right. So, that is something like this. Okay. So, that is the case. Is it clear? Okay. Now, can someone just look at it for a minute? Can you comment on this graph? There are very interesting things there. There are very interesting things. One is, number one, is that yes, there is a constant, there is a linear variation, that is very clear. But apart from that, there are other things as well. Can you look at that graph and tell me? Just take a minute to look at it and tell me. Beautiful. So, in other words, that is very good answer. In other words, what it means is that there are points where the solution is very accurate. Okay, there are points in this particular bar where the solution happens to be very accurate. Later on you will see that in finite element analysis also there are points where the solutions are very accurate, and these points are called as super convergent points, right. Okay, that is a very interesting result. Okay, so these two are very interesting, but the point you may ask is, how many terms do I take? Do I take only one term, two terms, or three terms? Okay, and number two, whether I can take only x cube terms, from x cube terms onwards, what will happen, and so on. Okay, these are some of the questions you may ask. So there are some rules for writing down the displacement functions. Number one, the displacement function should be complete. Should be complete. What does it mean? It means that if I take a higher order term, x squared term, then I should also take the linear term and so on. So why? Because for example, if I had started this whole exercise of writing u in terms of x power 4, if I had taken this in terms of x power 4, what would have happened? Beautiful. So we wouldn't have got the solution at all. So it is important that we have a complete series. So if I take x power 4, I should also have x term in it, x squared term in it, x cube term in it, and only x power 4 terms. So it should be complete in that sense. Yes, I can leave out after a1 and a2, I can leave out other terms, it does not matter, but I can't go to the n terms, like after cube or terms with higher order terms, and then leave out lower order terms. Number two, the u should be continuous. Whatever I choose, the u should be continuous, okay, and should be single valued. In other words, then only it will give you compatible result, right. It should be a single valued function, okay, that is important, right. So these are, I mean, we are going to expand this conditions later when we go to the second degree and so on, but right now it is important to realize that this is the one. These are the two important conditions. Now let us again look back this curve, look at this curve, okay. Now look at this curve. There is one more thing that you would notice from this curve. What is it that you notice? That the displacement that we have arrived at is lower than the actual displacement. The displacement that we have arrived at is lower than the actual displacement. In other words, what does it mean physically? No. What does it mean physically? Physically it means, yeah, that's it. Physically it means that the stiffness is more. The stiffness is more when is that? When I restrict the degree of freedom. See, obviously in a one term solution I had only that a1 fellow, okay. On the other hand, when I make it two terms, a1 and a2, okay, I had two chaps to really tell me how displacement takes place. So lesser the degree of freedom, more stiff it becomes, and hence the displacement terms are smaller, okay, or displacements are smaller. Another thing you should notice very carefully between the two graphs, what is that? Between this graph and this graph, what is that you notice between the two? Please notice that displacements are much more accurate than the strains and the stresses. Notice that displacements are much more accurate than strain and stress. Obviously this is the same as stress or strain, it is all the same, only thing is I multiplied by E, but in other words u is much more accurate than its derivative, okay. And notice one more thing carefully, these observations are very important because we are going to extend this same observations into finite element analysis, which is nothing but a small extension of the Rayleigh-Ritz principle. Okay. One more thing, can you notice from the stress graph, you see that at the end, okay, stress is not 0 as is shown in other cases. So in other words, stress boundary conditions will not be exactly satisfied, but will also be accurately, not accurately satisfied, but also be approximately satisfied. Okay. Now, in fact, you can look at Rayleigh-Ritz procedure, what we have done in another sense, in the sense that we do Rayleigh-Ritz procedure by assuming as if the whole body is one element. So now finite element can be looked at as a Rayleigh-Ritz procedure with the difference that we split up the body into a finite number of elements and start writing down this kind of equations for every element. Okay. So there is quite a unity between finite element and this Rayleigh-Ritz procedure, because both of them are approximate, both of them try to write down the displacement conditions in terms of certain other factors like A1 or U1 and so on, and both of them rely on, say for example, potential energy, minimization of potential energy principle. Is that clear? Okay. We will start the derivation for finite element analysis from potential energy principle in the next class. But meanwhile, if there is any question, I can answer. Is this procedure clear? Okay. So what we are going to do is to extend this procedure and apply it to a number of elements. I know that the criticism, as someone said, that A1, A2, what is A1, A2, A3, okay, that is not very clear. Okay. That is exactly what we are going to address when we go to finite element, or in other words, what we are going to do is to replace this degrees of freedom A1, A2, A3, which does not seem to have any physical meaning, by means of degrees of freedom of the nodes, which seems to have much more, or which looks like it has a much more physical sense rather than yes. Okay. Now how are we going to derive this? We will see that in the next class.